So I think you get the notation. I think you understand how to look at notation and tell when you're adding functions or subtracting functions or multiplying functions or dividing functions. But what's just as important as understanding the notation is understanding what you do on the graph. It's always the y coordinates that are being operated on. So if you're multiplying two functions together, you look at a particular location for x and you multiply the y coordinates. What that leads to, everybody, is that the only way you can perform the operations on the y coordinates is if the y coordinates are there to be operated on. And what that means is that the only way you can perform the operations is if the function is defined, if both functions are defined in that region. And what that leads to is this domain rule, that the domain of the product of two functions, or the domain of the sum of two functions, or the domain of the difference of two functions, is whatever domain is common to both. And then we just add another layer on. If it's a quotient of two functions, it's the domain that's common to both, but then we have to remove from that any non-permissible values, which corresponds to the function you're dividing by. I guess that's called the divisor. Any values of x that make the divisor 0 are excluded from the domain. All right, take a look over your work, please. Does anybody have any questions here that you would like me to go over from this section? 10A. 10A? Kind of a high-level question, all of question 10 is, because it combines trigonometry, which is always, for a lot of us, difficult, challenging, with the idea of, in this case, a quotient of two functions. And you're asked to state the domain and range of the combined function and also state any restrictions. So in question 10a, if we want y equals f of x over g of x, and you will notice, everybody, that as soon as I looked at this is my eyeball, as soon as I looked at that, my brain processed it into, oh, it's f of x over g of x. I just see it that way. F of x is tangent of x, g of x is cosine of x, so now you're dealing with tangent of x divided by cosine of x. And what are we asked for? We're asked for the domain. Well, let's start with the domain. The range, by the way, remember, there is no range rule. As many different functions as there can be that many different ways of finding ranges. There's just a multitude of doing it. And it's not a matter of you can always do it this way or always do it that way. But the domain is the domain that's common. Now, when you take a look at the graph of y equals tan of x, tangent of x, I'm going to go in degrees here. Tangent of x is not defined at 90 degrees or at 270 degrees. That graph has vertical asymptotes at 90 degrees and 270 degrees. And the reason for that is when you get up on the unit circle to 90 degrees and you want tangent, tangent is y over x on the unit circle. But at 90 degrees, and you have a diploma exam in 6, 7 weeks, whatever it is, 5 weeks, when you're at 90 degrees, the x coordinate on the unit circle is 0. So y over x is going to be undefined. And, you know, not that it really matters, but what the graph ends up looking like is it has these curves. I don't know if you remember that or not. But the domain of tangent of x is x cannot be equal to 90 degrees or 90 degrees plus multiples of 180, which would be at the top of the unit circle and then all of the bottom points of the unit circle, regardless of the rotations. What that tells us, Jason, is the domain here is x is not equal to 90 degrees plus multiples of 180 degrees. When you take a look at the domain of cosine of x, I'm not going to sketch it. Cosine of x starts at 1 on the y-axis and wobbles up and down in both directions between positive 1 and negative 1 vertically. The domain of cosine of x is any real number. So the overlap of those two domains would be x is not equal to 90 degrees plus multiples of 180. So this is actually the domain. X is not equal to 90 degrees plus multiples of 180 degrees. I guess I should say that n is an element of the integer number set, but no, there's no but about it. I should say that. I'm not sure why it says and any restrictions. The domain is a statement of restrictions. It's telling you what x is not allowed to be. In terms of the range, I can address it briefly, but I will tell you it's unimportant. Since tangent has a range of any real number, and this isn't an overlap, this is something different. Since tangent has a range of any real number, it's going to have infinitely large values for y and infinitely small values for y. And by infinitely small, I mean stuff like negative infinity. Okay? And cosine, again, cosine wobbles up and down between 1 and negative 1. But if I take this range of numbers between 1 and negative 1 and start multiplying it in various places by infinitely large and infinitely small numbers, I'm going to get infinitely large and infinitely small numbers, which means whatever this graph looks like, it's also going to extend vertically across all real numbers. But I wouldn't lose any sleep over that. Okay, that's not at all the point of this. Does that answer your question? Okay. Any other questions? Go ahead, Ryan.
7D.
Did you say D? Okay. 7D. So, and we did talk about one like this yesterday, I think. But it was a sum and difference function. I think, Farhan, you had asked about one like this. And when Farhan asked his question yesterday, I said, normally you're given the two functions and asked to find the sum, or the difference, or the quotient, or the product. And that's not what's happening here. We have h of x equals f of x times g of x, and we're not told f of x and g of x. What we're actually told is f of x, and we're told h of x. H of x in D is 10x squared plus 13x minus 30. F of x is 2x plus 5. So now, going back on what I said yesterday, Farhan, I think now is the time for the algebraic approach. You can't just look at that. Well, most people can't just look at that and tell me what g of x is. If we rearrange this, Ryan, for g of x, we're going to have to divide both sides by 2x plus 5. And then you're left with g of x is equal to that. But we always want to simplify our results. How do we simplify that? Well, it's a rational expression. You have to factor everything completely. This is from Math 20-1 before you can cancel. I'm going to guess, I'm going to go out on a limb here and say that one of the factors is going to be 2x plus 5. Otherwise, kind of what would be the point of the question. If it is, and we want to get 10x squared on the top, I would need a 5x. And if we want to get negative 30 on the top, I would need a negative 6. Now, I can't go on faith alone here. I really should FOIL that out or do the outer inner thing to confirm that I get 13x, and I do. My outer term will be negative 12x. My inner term will be 25x. 25x plus negative 12x is 13x. So what we get is g of x is equal to 5x minus 6. Good? All right. Let's move on. We've got 2 more lessons to cover in this unit. I don't think it's page 16. I didn't change that. I think it's probably page 15 or 14. 15? Yeah. So it's on page 15 of your unit handout. And just out of the gate, I want to let you know that a composite function is something entirely different. It's a different beast than adding functions or subtracting them or multiplying them or dividing them. It's something entirely different. We're going to learn a lot about composite functions today. We're going to be determining values of composite functions for particular inputs. And I'm going to use that word a lot today. Write the equation of a composite function and state any restrictions, which means we're really talking about domain. The domain rule doesn't apply here. When you have two functions that get together as a composition, whatever that is, when you have two functions that get together as a composition, the domain is not determined by looking at the common domain. And then we're going to be sketching the graphs of a composite function. So I'm going to spend some time reviewing here what a function is. And this is taught to you in grade 10. Mr. Hetlinger, do we do function notation in grade 10? We do. So we introduced the idea of functions in grade 10. I think in grade 11 we don't really use it a lot. It just kind of falls by the wayside. And then all of a sudden it becomes important in grade 12. But a function is an operation performed on an input that results in an output. And it results in a single output. Now, input, and again, focus up here. Don't worry about the numbers and everything on your handout just yet. The input is something that we typically call x, and the output is y. So the fact that I have the word single there is what makes this mathematical relation specifically a function. It's that for each x that goes in, you get only one y coming out. You only get one output, which means if you were to plot all the points, it would pass the vertical line test. Keep in mind that we can say the output is y, but I can also say the output is f of x because y is equal to f of x. And then we find ourselves going around in circles again with all these definitions. Just consider the function for a second, and this is very basic stuff, but it's going to get complicated today, and if you understand the basics, you will understand the complicated material. At least you'll have a better chance. So consider the function f of x equals the square root of x. What's the function? The function is square root. That's the mathematical operation that's going on in terms of what we're doing to the input, which is the argument. So to find a value of y, you need to put the value of x into the function. So this flow diagram that I've got is crucial today. We put x into a function and y comes out. So if x is equal to 4, we run x equals 4 through the function. Notice that in the top line it says f of x equals root x. So when I put x equals 4 in, every x in what I've written becomes a 4. It's no longer f of x, it's f of 4. And it's no longer root x, it's root 4. And we figure out what that is. The principal square root of 4 is 2. And I know this is very elementary. If I were to say what happens when we put 9 in, then I'm asking you to figure out f of 9, and we replace all of the x's with 9, and you get the principal square root of 9 is 3. X equals 1, that would be f of 1, which is root 1, which is 1. So this is the idea behind a function. So first of all, I want you to understand that this question here is not a Math 30 question. I'm getting you to understand the concept of a function. It's a rule. In this machine, this is the function, some kind of machine. I throw an input in, it does something mathematically to that input, and it spits out an output. And if I said to you, what is happening to 3 to get 8, you might, just looking at that alone, say, well, I'm adding 5. But if the function is taking 5 plus the input to get the output, then we should be getting 10 over here, and we're not. So I want everybody to think for a second, and again, what I'm asking you to do is not a Math 30 question. I'm just asking you to warm your brains up. What is happening to x in all of these cases? Up top, in those first 3, what is happening to x to produce y? How many of you have it? I'm not asking what it is. Usually, if you don't get it, and again, this isn't the point of the lesson, you might want to try doubling the input and seeing what you would have to do to get the output. So if I double 3, I get 6. I'd have to add 2. If I double 5, I get 10. If I add 2, nope. What is it, Makai? Right. What's happening, the function, the operation on the input is you're tripling the input and you're subtracting 1. So we could even cut to the chase down here and on the bottom say when we put x in, you get 3x minus 1. Which means f of x is 3x minus 1. And we could figure out these other ones. If I take 3 times 9, I get 27 minus 1. I'm not using a calculator. I'm using my automatic pilot mode in my head. So if I make a numerical mistake, please check me. Negative 4 times 3 is negative 12, minus 1 is negative 13. I think those two are right, though. Okay. So that's what a function is. A function takes an input, applies a rule to that input to spit out an output. So this function is written as f of x equals 3x minus 1. And I'm going to be showing you some stuff up here that's not necessarily in your note package. All right, moving on. What a composite function does is it takes two functions and links them together as a chain. And what happens is you put an input into the first function, and whatever the output of the first function is becomes the input of the second function. So it's two functions being performed on an original input, but the first function changes that input to a different number, which is the output of the first function, and that output of the first function becomes the input of the second function. Okay? So, as an illustration, and this is not in your notes, okay? I'm just asking you to just relax and think about what I'm going to tell you. If I have a function that is the function called f, and the function is subtract 3 from the input, in other words, f of x is x minus 3. And I have a different function, g, which is to square the input. That would mean g of x is x squared. And I put them together as a composite function. This whole thing is a function. With an input and an output. But the function itself has multiple stages to it inside. The first thing that happens is, and we can pick a number here. Give me a positive number less than 10, Ben. 6. So if I were to choose 6 as an input, and I subtract 3 from the input, that gives me, and I square the input, which is really the output of the first one, that gives me 9. That's what we're talking about doing. Let's go with the same input, but I'm going to switch the two functions. So what if I said, let's look at this composite function, where the input is squared first, and you said 6? What would be the output of the first layer or stage of this function? 36. 33. So one thing I'm demonstrating with this little example is the order in which you compose the functions makes a difference, doesn't it? When we talked about putting, and now I'm going to introduce a little bit more of the function notation, when we talked about putting f of x into g of x, we got 9 when we used an original input of 3. But when we talk about putting g of x into f of x, we don't get 9, we get 33. If you were to look at the front cover of your unit handout, that's what that picture is all about. And this is way beyond where we're at right now, but if I have f of x and g of x as graphs that look like that, it turns out that when I put this bottom one is putting f of x into g of x. The top one is putting g of x into f of x. Don't worry about the notation, but it makes a difference. It matters. All right. So what's going on in these functions? So now I've linked pairs of functions together, g of x and f of x together. Just take a minute here and see if you can figure out what g of x is doing to x to get the output in g of x. And again, I don't want to spend a lot of time with this. It's just a puzzle more than anything. How many of you see pretty much immediately what it is? Liam, do you got it? What do you think it is? I think it's 4x plus 1. 4 times 0 is 0, plus 1 is 1. 4 times 2 is 8, plus 1 is 9. 4 times negative 3 is negative 12, plus 1 is negative 11. It's working. I hope it's really clear what f of x is. F of x is squaring the input. So what are we asked to do here? We're asked to complete this. So we said that g of x, and I'll just write it up here, g of x was 4x minus 1. F of x was x squared. I put negative 2 in. And let's see, negative 2 times 4 is negative 8 minus 1 is negative 9. Am I correct? Now I want you to notice something, because this is going to cause confusion if you don't get it cleared up right now. That negative 9 is both a y and an x. That negative 9 is a y value in g of x, but it becomes an x value in f of x. Yeah. Liam had figured out that that's what we're doing to this number to get that number in all of, oh, is it plus 1? It's plus 1? I'm sorry. So that clears up your question then. Okay, that's my mistake. It's plus 1. I'll put that in red. So this, I'm sorry, is negative 7. Is that better? Okay. So we get negative 7 here. That negative 7 is an x coordinate on f of x because it's going into f of x, but that negative 7 is a y coordinate on g of x because it comes out of g of x. So think about this graphically. That means if you ever have to work with data points, you're going to find the original input as x, read the y coordinate of that on the first function, then take that y coordinate and locate it as an x coordinate on the second function to locate the y coordinate there. It's not you're just adding or doing something to y coordinates. It's x becomes y, the y turns into an x, and you find a new y. 4x plus 1 gives me 13 here. 4x plus 1 gives me 41 here. I have to square negative 7, so I get 49. I have to square 13, and I get 169. I'm a little embarrassed to admit that I don't know what 41 squared is. I want to say 480. Well, I don't know. I'm just guessing now. 681? I don't know. 1681. Boy, was I ever off. Well, of course, 40 squared is 1600, so 1681. So what is f of x? And this isn't the goal here. I mean, we figured out, I got to be careful about the order here. F of x was x squared, right? F of x was x squared. And I would expect everybody to see that it was x squared. You're squaring the inputs to get the outputs. This one was 4x plus 1. And I wouldn't expect you necessarily to be able to figure that out. I don't think it's a difficult problem, but it's not a Math 30 problem. Okay, that's not the goal here. The whole purpose of these little machines that I've drawn for you is to help you understand how functions work. So number 2 says, write the equation h of x that converts the first input into the second output in this diagram. So when we put in x, what does g of x do to x? Well, g of x turns it into 4x plus 1. What does f of x do to 4x plus 1? Well, see, 4x plus 1 is the y coordinate out of the first function, but it becomes the x coordinate in the second function. So what's going to come out is 4x plus 1 squared. It's no different than if we had a number going in, except that it's not a number, it's x. And what that means is that h of x in this example, which is the result of putting g of x into f of x, is 4x plus 1 quantity squared. I don't think there's really any need to simplify that, but if you wanted to, you could FOIL this out. Meaning, think of it as 4x plus 1 times 4x plus 1, and do your foiling, your distributive property of multiplication. Any questions with number 2 here? Okay. So, what we just did by putting g of x into f of x is written this way. Look at this. Let me just try something here. If I said to you, what is f of 5? Then you would put 5 in for x in f of x, correct? If I said to you, what is f of hearts? You would put hearts in for x in f of x. So what did we do here? What did we put in for x in f of x? We put g of x in for x in f of x. This is g of x. It went in wherever there was an x in f of x. And that's why this function can be written this way. It's f of g of x. Are you with me on that? Well, we write it this way. That f with the open dot and then the g of x means f of g of x. This function goes into that function. It's going to be very easy for you to get the order mixed up from time to time. It's the second function in the function notation that goes into the first one. And that's called a composite function or a composition of two functions. Does anybody have any questions with that notation? Go ahead, Grant.
Does it matter if g of x is f of x?
Yes, it does. Because, and you know what, maybe I will cut to the chase here and talk about this. What did we do here? Did we put g of x into f of x, or did we put f of x into g of x? We put f of x into g of x, right? So f of x went into g of x, which means that this whole thing is g of f of x. F of x went into g. I'll get to the other notation in a second. This one, we took g of x and loaded it in for x in f of x, which means this whole function is f of g of x. And boy, when I teach this, I have to look every time because it can be so simple to just get the order wrong. So your question is, does it matter which letter comes first? This would be written as f of g of x. The f comes first because g went into f. And we get 33 as a specific number here, whereas this one would be written as g of f of x, because f goes into g. Have I answered your question, Grant? Perfect. Any other questions with this notation? Any other questions with this notation? Okay. So the composition of two functions is a new function found by substituting g into f, if it's f of g of x. For example, and I don't believe this is in your notes, okay, but just looking up here. If I had, is this in your notes? It is. Is it all typed out already? Okay, good. If I had f of g of x here, what does that mean? It means that. And I know that most of you probably get this, but I really want to make sure everybody gets it. If I said, what is f of 3? Then you would put 3 in for x in f. So if I say, what is f of g of x, then every place there's an x in f, every place there's an x in f, we're going to put g of x. So if f of x was 3x minus 2, f of g of x is 3 times g of x minus 2. And since g of x, keep doing that, since g of x is x plus 5, I load it in, and the rest of this is just a matter of simplifying it. So f of g of x is 3x plus 13. Still with me? Okay. Well, here's a question for you. Find g of f of x with the same functions. I just showed you how to find f of g of x. You substitute g of x in for x in f of x, and you simplify. What I want you to do, and I'm going to give you a minute to do this, is find g of f of x. I'll write this out first to help you get started. G of f of x means that. The math isn't complicated. It's sorting out in your head what it is you should be doing. What this is saying is you're going to take f of x and you're going to put it right here. Every place there's an x in g of x, you're going to put f of x. So what we're going to get is g of f of x. I guess I'll just write equals 3x minus 2 plus 5. And I'm going to really think about this, because as soon as I start writing it, I lose the logic that I had and it doesn't make sense to me. So I have to say to myself, g of x is the input plus 5. So g of f of x will be f of x plus 5. And we get 3x plus 3. Get the same answer? Okay. It's slippery. Intellectually, it's very easy to lose track of what's going on here. All right. Now some examples. F of x equals 4x, g of x equals x plus 6, h of x equals x squared. So what is f of g of 3? What is f of g of 3? And that could be written, by the way, as f of g of 3. So don't write anything just yet. Let me explain this. G of 3 is what comes out of G when you put 3 into G. I mean, I can see what G of x is. G of x is x plus 6. So I hope everybody knows that G of 3 is 9. 3 plus 6 is 9. But the bigger, broader point I want to make is to find G of 3, you run 3 through G and see what happens. So f of G of 3 means we're going to take this G of 3 and run it through f. And now you can start writing this. What we're doing is we're running 3 through the function G. Then we're taking whatever we get and running it through the function f. And the functions themselves are not difficult. When I put 3 in for x in g of x, I get 9. And when I put 9 through f of x, which is 4x, I get 36. So the answer is 36. Now I have a better diagram. That was just for explanation purposes. I would clean this diagram up and I would have said it this way. What you do is you run 3 through G to get a result. You run that through F to get your answer. That's kind of the template of what's going on here. So B, what is G of H of negative 2? Okay, so I have a question for you. I'm going to give you 2 options here. One of these is correct and one of them is incorrect. And it goes back to Grant's question about, does the order matter? And the order matters. Do I put the negative 2 through the function h first and then through g, or do I do it the other way around? Ben, you want to take a crack at it? Second one, definitely. It goes from the inside to the outside. You put negative 2 into h. Oh, you get 4. Right? You take 4 and put it through g. You get 10. The answer is 10. 4 plus 6 is 10. That's it. That's really kind of the lesson. It's going to get progressively more complicated, I suppose, but that's the gist of it. What's h of 2? Why not? What's to say you can't take 2 and run it through a function and then take the result and throw it back into the same function? This is just saying 2 goes through h to produce some intermediate thing, which, again, I think this is important. This thing that I've got in that kind of cloud is a y coordinate coming out of the first function, but it becomes the x coordinate going into the second function, which also happens to be h. I would caution you, many of you don't need this diagram, but every now and then it's helpful. So I put 2 in for h, I get 4. I put 4 in for h, I get 16. Any questions so far? Okay. Example 2. This is where things get complicated. What is f of g of x and what is g of f of x with those 2 functions? And I'm going to remind you of something. You learned this with rational functions last year and with rational functions in Chapter 9 this year, that even though you can simplify a mathematical expression, that should not remove any restrictions that were there to begin with. If you have a rational function with x minus 3 on the bottom and x minus 3 on the top, x cannot equal 3. It doesn't matter that you cancel them. Those restrictions stay in play. Keep that in mind. So what is f of g of x? Okay, wait a minute. This is complicated. I find it complicated. I need to look at it this way, and I need to say to myself that what that means is I'm going to take g of x and throw it in to f of x wherever there's an x. So f of x is the square root of the input minus 1. And the input is g of x. So f of g of x, and I'm just double checking, means we put g of x in for x in f of x. And we get that. Any questions with f of g of x? Now, what about g of f of x? Well, g of f of x, maybe what I'll do here is just highlight something for you. I think you guys get this, but this is found by taking this and putting it there, right? G of x goes into f of x. On the other hand, this is found by putting f of x into g of x. So it's found by taking this and putting it in there. Which means we're going to have, so I should close my brackets here, root of x minus 1 squared, which is not x minus 1. It's not. I can demonstrate to you that it's not x minus 1. I know you're taught that these two operations should cancel each other, right? Square root, squaring, they should cancel. But if you think it's x minus 1, then what that means is you're saying it looks like that. You're saying this function is a straight line that extends forever. But the fact of the matter is, it is that's how you would have to enter this, because you're taking the square root of x minus 1 before you're squaring it. And I know that you're thinking, well, why should that make a difference? Okay, but we have to square the square root, not square root the square. Although it probably in this case wouldn't matter. But when I take a look at this graph, that's not x minus 1. That's not x minus 1. Now, why is that the case? Well, let's talk now about the domain of these functions. So the domain of f of x is greater than or equal to 1. There's many ways we could figure out the domain of that. You could probably do it with transformations, or you could say that the radicand must be greater than or equal to 0, because you can't take the square root of a negative. That leads you to x is greater than or equal to 1. G of x equals x squared. This is any real number. It's grade 11 math. Now, what is f of g of x for a domain? Think about this for a second. F of g of x means we take x and we put it into g of x first, which was, I gotta look now, which was x squared, and then we put that into the next function, which was the input minus 1. Okay. Is there any value of x that you are not allowed to square? No. So this line from x to x squared doesn't have any restrictions. That means we can cut to the chase and look at this function. And I know this seems kind of weird, because you might say, well, why don't we just look at it anyway? Maybe this first stage has a roadblock that blocks a whole bunch of x's out from even getting to the second stage. So how are we going to determine the domain of this? Well, I'm not really that concerned about it, but I will show you. Last year you learned, actually this year you learned about square roots of functions. And you learned that if you have x squared minus 1, which you know what x squared minus 1 looks like, and you square root it, you get invariant points where y is 1 and 0, because the square root of 1 is 1 and the square root of 0 is 0. And you get, this goes back a long time ago in this course. Do you remember doing that? Well, those two x-intercepts are -1 and 1, which leads us to the solution for the domain. And you know what I'm telling you? I don't think you need to worry about algebraically finding the domain of this function. You can look at the graph. So the domain here is for f of g of x. The domain is x is less than or equal to -1 and x is greater than or equal to +1. Now, when you take a look at g of f of x, the first thing you do to x is you run it into the square root of x minus 1. And then you take the square root of x minus 1 and you run it into the input squared. Is there any roadblock at the first stage? Is there any value of x that's not going to be allowed into the first stage? Well, definitely, because the domain of that first function is x is greater than or equal to 1. So as soon as the x's get here, the only thing that comes through is anything that falls into that domain. Now, whatever comes out, will you always be allowed to square it? Sure. So the only issue, the only gatekeeper to remove x's from the domain of all real numbers is that first stage, which means that this is the answer to the question for g of f of x. That's confusing. By the way, that's why the graph only starts at x equals 1. By the way, if I switch the order of those operations, if I squared x minus 1 first and then took the square root, you might ask yourself what's going to happen then. All right, let's go through a bunch of other quick questions here. Example 3. F of x is x plus 1, g of x is x squared. I meant to remove this from your notes. This is from a couple of years ago, and I changed the version a couple of years ago, but for some reason this was still in my version that I printed. I'm not concerned here about a rough sketch of the graph. We can talk about it if it comes up, but it's not important. F of g of x means g of x goes through f of x to get our answer. That's another way to look at this. G of x goes into f of x. So it's pretty clear you're going to get x squared plus 1. Inner function goes into outer function, always. What is g of f of x? Well, that means that f of x is going to go in to g of x, which means it's going to be x plus 1 quantity squared. If you choose to FOIL that out and write x squared plus 2x plus 1, you can. By the way, the reason why I'm not concerned about the graphs here is you should know what x squared plus 1 looks like as a graph. It's a basic transformation of the starting parabola, y equals x squared. You should know what x plus 1 quantity squared looks like. Don't mistake what I'm saying here. I'm not saying you won't be asked for domain or range of these functions on an exam. I'm saying it's something you know how to do. So an exam question might be, what is the domain of g of f of x? So you have to develop this function and then use your knowledge from previous courses. F of x. Now things start to get a little bit challenging. What this is saying is, let me write f of x bigger. F of x equals x plus 1. What this is saying is, this function is going to eat itself. This x plus 1 is going to go in for x in f of x. So we're going to have f of x plus 1, which is f of x plus 1, which will be x plus 1 plus 1, which is x plus 2. This is f of x. It's confusing. It really is confusing. To me, anyway. I'm always kind of walking on eggshells here thinking I'm going to make a mistake because it's confusing in my mind. So if it's confusing to you, then you're not alone. G of x. We're going to take x squared and put it in for x in x squared, which means we're going to get, well, g of x is input squared, but our input is g of x. We're going to get x to the 4. That's it. I want you to get lots of practice here, but I want to just, before I give you the assignment, talk about number 1 here, because some people, as soon as I give the assignment, they go, I don't know what's going on now. If you take a look at number 1, just up here. If I said to you, given all that information up top, what is f of g of 2? Then what I'm asking you to do is run 2 through g to figure out what g of 2 is, and run g of 2 through f to figure out what the answer is. But we don't have an equation. We don't even have a graph we can look at. But you're told g of 2 is 5. So you need to know that if g of 2 is 5, that's a way of saying when you run 2 for x through g, you get 5. And then, if you want to know the answer, if you're going to put 5 in to f, then you need to know what f of 5 is, and you just look up there and the answer is 0. So you don't need an equation necessarily to figure out inputs and outputs. They could be given to you as ordered pairs. They could be given to you as graphs. One last quick point, and then I will let you get to work. Oops. We're going to be doing a lot more of this tomorrow, but I want to introduce it to you now. If I gave you these graphs, and I said, what is f of g of 5, approximately, you should be able to figure it out. Because this is saying you need to take 5 and run it through g to figure out what g of 5 is, and then take that and run it through f to figure out what the answer is. So what does it mean to say I'm going to run g through 5? Well, it means if I had the equation for g, I'd put x equals 5 in, right? But I don't have an equation. However, I can look at x equals 5, and I can see that the output for x equals 5 is very approximately 2.1. Would you agree? Yeah. Sorry, 3.1. That's better. Would you agree it's pretty close to 3.1? So that would mean that you would say this is 3.1. Now, what do we do with that 3.1? We load it into f, but that means that 3.1 now, that means that 3.1 is now an x coordinate. And we're going to look at where the y coordinate at 3.1 is and get approximately 3.3. So again, you can figure out inputs and outputs by looking at ordered pairs, like question 1 on today's assignment. You can figure them out by looking at equations, or you could figure them out by looking at a graph if you ever need to. So, did that lesson make sense overall? Any questions? Okay. So, don't do number 7. Just 1 to 6 and 8, 9, and 10. And tomorrow we'll finish off with composite functions. We'll be done the unit tomorrow. Monday and Tuesday we're going to review, so your unit exam is on Wednesday of next week.